Good afternoon. Today we're going to start with section 1.1 and then eventually move into section 3.8, which is going to be our main focus today. Today there's only going to be one video because this topic is pretty dense and you might want to spend a little bit of time getting used to the idea of what's going on here. So let's go ahead and start with section 1.1, a review of functions. So what exactly is a function? A function f is a rule that assigns each element x in a domain to exactly one unique element in f of x in the range. So I've got my little drawing here. I've got an input. It goes into some black box. Maybe we know what happens, maybe we don't. And it goes to some output, f of x. So with a function, our domain is the collection of all the values we can put into our function. And this is where the independent variable belongs. So all of these values, everything that we can do here is an independent variable. Whereas the range is the collection of all of the values we get out of our function. This is the dependent variable. So typically we have an independent variable x, we can put something in, and then our f of x or y is our dependent variable. So quick question in an example, what is the domain and range of the function f of x equals x squared? Go ahead and take a moment, write this down, and meet me back in a moment. So the question was, what is the domain and range of the function f of x equals x squared? Now, f is defined for all values of x, therefore its domain is the set of all real numbers, or negative infinity to positive infinity. But because x squared will always be a positive value, no matter what x we put in, the range for this function is inclusive 0 to infinity. So note we have an open bracket around the 0 because we can get the value 0 out. And then we have infinity closed parenthesis. We're never going to get the value infinity because infinity is a concept, but that's okay. So this is how we write that. And this is to say that we can give f, our function, any number we want, but we will only ever get a positive number out. So one way that you can tell if a graph represents a function is if and only if it passes the vertical line test. So we can draw our function however we want, and we have our friendly neighborhood function y equals x squared over here on the left-hand side. And if I were to draw any vertical line, it would cross my function only once, and that means it passes the vertical line test. So this graph represents the function y equals x squared. Now, let's consider the graph of the function x squared plus y squared equals 1. Because when I draw my vertical line, I intercept my graph twice, this is not a graph that represents my function. So this is not valid. And it fails the vertical line test. So now that we know what the vertical line test is, we can get to implicit differentiation. So this section is devoted to calculating derivatives of functions of the form y equals f of x, where y is defined explicitly as a function of x. So explicitly means one value of y equals some combination of values of x, maybe composition, maybe sums, products, we don't know. But think y equals x squared. I've got one way to map x to y. But often relationships are expressed implicitly. This means that though I have a y and I might be able to solve for it, that's not how my function is given to me. So think x squared plus y squared equals 1. This is the function that describes the unit circle with radius equals 1. So I could solve for my y term, but y is mixed up here. It's added together with x squared. My y term is squared, and it equals some value 1. Now, in order to get an explicit definition, we can solve for y to get explicit equations. So our first step is to move our x squared to the right-hand side. Then we can take the square root of both sides, and we get y equals positive 1 minus x squared quantity square root, or negative 1 minus x squared quantity square root. So in this uppermost graph, we have our original function, x squared plus y squared equals 1, and we can see that it fails the vertical line test. But when we go and solve for y and we get two unique equations, 1 minus x squared quantity square root, that function passes the vertical line test. Anywhere I've got red, I can draw a vertical line in green, and it will only cross the function once. And we also get the negative version of that. So that's my graph here in blue. And together with these two separate graphs, we end up with our unit circle together. And this one passes the vertical line test, and that's exactly what we want. So now that we have y defined explicitly, one value of y equals some map from x to y, we can solve for their derivatives. So dy dx of our first expression equals x divided by square root of 1 minus x squared, and dy dx equals negative x over 1 minus x squared quantity square root. And that's pretty simple. Now, for y squared plus x squared equals 1, it's pretty easy to solve for y, but this is not always the case. Sometimes things are more jumbled up. Maybe we have cosine of x times y equals x squared plus y squared. There's nothing we can do to separate our x's and our y's from one another. So can we find a single expression for the derivative directly from the equation without first solving for y? And the answer is yes. And this technique is called implicit differentiation. And the best way to go about showing you how this works is to do examples. So I've got a couple examples built in here that we're going to go through really, well, not quickly, but we're going to go through them. So the first example is to calculate dy dx directly from the equation of our unit circle, x squared plus y squared equals 1. Now, you don't have to pause. You can just continue watching this video since this example is the way to teach you the method. So first, we replace y with y of x to make it clear that x is our independent variable. So now I've got x squared plus y of x quantity squared equals 1. Next, we take the derivative and we respect the chain rule. So this first one, d dx of x squared, that's pretty simple. But our second term, d dx of y of x squared, we're going to want to say derivative of the outside, so 2 comes down in front, times y of x, 2 minus 1 is 1, times the derivative of the inside, and our inside function is y of x. Now, we don't know what the derivative of y of x is yet. That's what we're trying to find. So we can just leave it in the form y prime of x. And then we know that d dx of a constant value is equal to 0. So altogether, our derivative of our expression is 2x plus 2y times y prime equals 0. Finally, our goal is to find the derivative, which is dy dx, so we're going to solve for y prime. So we move over our 2x onto the right-hand side, and then we divide each side by 2y. Our 2's cancel out, and we're left with dy dx, or y prime, is equal to negative x divided by y. Now, this example continues. There's more to it that I want to make sure you guys understand. So using the results from the previous slides, find the slope of our unit circle at 1/2 square root 3 over 2 and 1/2 negative square root 3 over 2. So go ahead and continue with me. The derivative dy dx equals negative x over y depends on both x and y. So to find the slope of our circle at 1/2 square root 3 over 2, we substitute in both x equals 1/2 and y equals square root 3/2 into our derivative formula. So I've got dy dx and one single absolute value bar, and at the bottom, the points I'm plugging in, equals negative 1/2, that's my x value, divided by my y value, square root 3 over 2. My 1/2s cancel, and I'm left with negative 1 over square root 3. So what about the other one? Well, that's just going to be the positive version of this. So I see here I've got my unit circle, and we can pretend that we've got the red arc on top and the blue arc on bottom, and the slope of the line, that slope of the tangent line at 1/2 comma square root 3 over 2 is negative 1 over 3/2, or 1 over square root 3. Whereas conversely, for the point 1/2 negative square root 3 over 2, our slope is positive. It's 1 over square root 3. So there's one more example I want you guys to see before you really understand what we're doing here. So let's find y prime when our function is sine of xy equals x squared plus y. Now, for our previous problem, it was pretty easy to see that we could solve for y and then go about and find our derivatives. But in this one, there's nothing we can do to separate our xy term inside the sign from our x squared plus y term on the right-hand side. So maybe see if you can at least take the derivative of each side and then meet me back for the second half of this problem. So with our example, I want you to find y prime of x when our function is sine of xy equals x squared plus y. Now, using the chain rule and the product rule, we get cosine of xy times y plus x y prime is equal to 2x plus y prime. Now, our goal here is to isolate y prime. So we want y prime on one side and everything else on the other side. So we can expand our first term and then try and solve and get all of our y primes on one side and everything else on the other side. So we're left with x y prime times cosine xy minus y prime equals 2x minus y times cosine xy. On the left-hand side, we can pull a y prime out, and then we divide our right-hand side by everything that's not y prime on the left-hand side. Our y prime, or our dy dx, is equal to 2x minus y cosine xy. I need to fix that because that should be cosine xy, divided by x cosine xy minus 1. So that's the presentation for today. Remember, this is the only work you have to do today. So if this doesn't make sense, go ahead, slow it down, put it on half speed maybe, send me an email, watch the video one more time, and work through these examples as I work through these examples and see if you get the same results. All right, that's it for me today.